Okay, this first one up here, how do we calculate out what the pressure that the helium is providing? Okay, so I know the argon's providing 3 pounds, or 3 atmospheres, and that the total pressure is 9 atmospheres, so then it's just 6 atmospheres? Okay. What else does that tell you about the particles, the gas particles? Do you have any other piece of information? Yeah, you do. From this, you know something else. Totally know something else.
Could you find out how many moles?
You know that there are twice as many moles of helium than there are argon. We okay with that? Twice as many actual particles. Not necessarily, and definitely not twice the mass. It's actually going to be a considerably lot less mass because the helium's a 4 mass and the argon's a 40 mass. But there are literally twice as many helium particles if the atmospheric pressure is double. Using that same canister, if you know there's about 40 grams of argon, how many grams of helium are in the canister? Remember what provides pressure. Okay, so if I've got 40, so this is like a 40-ish. If I've got about 40 grams of argon, the ratio is 1 mole of argon is about 40 grams of argon. So we've got about 1 mole of argon in that container, right? So tell me about the moles and the mass of the helium. How many moles of helium must we have?
At least twice.
Not at least, exactly. So we have exactly, since the helium provides, how did I write silver? Since helium provides double the pressure, then this must have twice the number of moles of helium. So then my total mass is about 8 grams of helium, since each mole of helium has a mass of 4 grams. Okay, react 25 grams of tin, 4-fluoride with zinc. What are the products? How much of each product? What's left over? How much is left over? Okay. So it's tin 4-fluoride plus zinc, fluoride plus tin. I need a 2 here and I need a 2 here. Is that it? If I put a 2 there, then my fluorines are balanced, and I put a 2 there, and then my zincs are balanced. Okay. So how do I approach these problems? What do I do?
So you want to set them up, start with your grams, right?
Okay, grams of what?
Grams of tin.
Okay, so start with grams of tin 4-fluoride. Can I start with grams of zinc? I have to start with both of them, don't I? I do 1 railroad track with the zinc, and I do 1 railroad track with the tin 4-fluoride. So we'll go with 25 grams of tin 4-fluoride, 1 mole tin 4-fluoride. What do we got here? So tin is 118.71, and then my fluorides are 18.998403 times 4. So I get 194.704 grams. And for every 1 mole of tin 4-fluoride, I get 2 moles of zinc. Where do the 1 and the 2 come from in that part of the calculation? Yeah. So wait, I don't want zinc. My total bad. I want to calculate a product mass, and so actually I'm just going to go with 1 mole of tin because that'll be the easiest. And then it was 118.71 grams of tin. No. 108.71 grams of tin, and that's 1 mole of tin. Okay, so now the only thing I have left is grams of tin. So I've got 25 divided by the 194 times the 118. I get 15.2. Okay, so what did that calculation just do?
Just like again, it can be 15.7 before you run out of the tin fluoride.
When you run out of the 25 grams of tin 4-fluoride, you will have made 15.2 grams of tin. One more piece of information. What else? What's the other piece of information that you need that this requires?
So you can only make that much if you have the other,
I can only make that much if I have enough of the zinc.
yeah.
We don't know that yet. So this is just an assumption we make, but we don't know. So now we're going to do that and we're going to find out. So I'm going to take my 25 grams of zinc. For every 1 mole of zinc, when it's 65.39 grams of zinc, and 2 moles of zinc, and 1 mole of tin, and 118.71 grams of tin, 1 mole of tin. That'll be grams of tin. So I've got 25 divided by 65.39 divided by 2 times 118.71. $22.7 grams. All right, cool. So what did this just do for me?
Told you what your limiting reagent.
Okay. Let me ask that differently. That second calculation by itself does what?
Tells you that you can only make
22.7 grams of tin with 25 grams of zinc if you have enough.
Exactly.
fluoride.
You can make 22.7 grams of tin if you've got 25 grams of zinc and as much tin 4-fluoride as you need. So which one of these is the true statement? The first one, right? Whichever one is the smaller. So the moment that I've made my 15.2 grams of tin, what happens? I run out of tin 4-fluoride and the reaction just stops. So I can never make 22.7 grams. So that means I have no tin 4-fluoride in the container. I've got 15.2 grams of tin in the container. I've got some leftover zinc in the container, and I'm going to have, what else? I'm going to have to calculate how much zinc fluoride is going to be left in the container. So what do you want to do next?
Zinc with zinc fluoride?
No. You don't bother with the zinc anymore because it's not the limiting reagent, right?
Tin fluoride with zinc.
We could do that. Or since there's only 4 things in this equation, what could we do? So I started with, there was 50 grams of stuff, right? We okay with that? That's how much reactant I started with. So that means I got to have 50 grams of stuff when I'm done. So I start off with 50 grams, and what do I know happens to some of the 50 grams? No. Oh, okay. It's gone. It's gone. 25. Is that what we said?
Used from the tin fluoride?
Okay. So 50 minus my 15.2 grams leaves me with This leaves me with 34.8 grams And so now I have to take my 34.8 grams and subtract off my 25 grams.
Do you have to do another railroad?
I could do another railroad. Let's back this up for a second. Let me write down exactly what's in the container. I know that there is 15.2 grams of tin. We okay with that? I know that there is 0 grams of tin 4-fluoride. I do need to do another railroad. I need to take my 25 grams of tin 4-fluoride and 1 mole of, in this case I'm going to go, I'll go to zinc fluoride, and it's 65.39 plus 18.99, 8403 times 2. And that'll be 103.387 grams. And then for every 2 moles, I've messed this whole thing up. Totally messed this up. Why isn't somebody stopping me from being dumb? I have to do this thing right here exactly the same and then switch the other side. So all of this is going to be exactly the same. 1 mole.
But isn't the zinc fluoride the limiting reagent?
Yeah, that is the limiting reagent.
So why did you choose to use the limiting reagent?
That's the only thing that matters.
But
What?
isn't there 0 tin fluoride?
Correct. There's 0 grams of tin fluoride left. But I want to know how much of the zinc fluoride I made.
By doing this lower one, you're also saying if you have 0 tin fluoride, how much, not only tin, but zinc fluoride of the product you're making, right?
This first one up here, if I've got 25 grams of tin 4-fluoride and as much zinc as I need, I can make 15.2 grams of tin. The bottom one is if I have 25 grams of zinc of tin 4-fluoride and as much zinc as I need, I can make how much zinc fluoride. So that'll tell me exactly how much of the 2 products I'm going to make. Let's run through this and then we'll talk about it in a sec. So 1 mole tin fluoride, and then 2 moles zinc fluoride, 1 mole zinc fluoride, and then what did we say it was? 103.387 grams of zinc fluoride. Okay, so I got this 103, I'm going to multiply by 2, I'm going to multiply by 25, I'm going to divide it by 194.704, and I get 26.5 grams of zinc fluoride. All right, so I made 26.5 grams of zinc fluoride. So those things are in my container for sure. And then the thing that I have to calculate is what? How much zinc is left. I know none of my tin 4-fluoride is left, but my, my zinc is definitely left over. And I've got 15.2, so that'll be a 7.1. So I have 41.7 grams of product, and I put 50 grams of stuff in, so then that leaves me with 8.3. So there's leftover 8.3 grams of zinc, because 8.3 plus 41.7 equals 50. So that's the other thing that's in my container. So when this reaction happens, the tin 4-fluoride and the zinc react with each other. And what runs out first? The tin 4-fluoride disappears. The moment the tin 4-fluoride disappears, how much tin was made? 15.2. How much zinc fluoride was made? What does this 22.7 got to do with this problem? Nothing. So I would, once I've determined which is the limiting reagent, I ignore the thing that doesn't run out because I don't care about it, because I can't actually make that much using that stuff because my other thing runs out first. You don't seem happy with that, Katie. That doesn't sound good enough. If on that third railroad track I would have used the zinc again, why would that not have helped me?
But how do you know that the zinc doesn't transfer in for the zinc fluoride? Would it be different?
I don't know what you mean by that. Well, transfer in would be different?
But if it's 25 grams of zinc, would it maybe, does it have more zinc fluoride for, would it make more zinc fluoride than it would?
It can't. Why can't it make more? Why can't I actually make this 22.7 grams of tin?
But what if the zinc fluoride is less than the zinc?
We don't care about the zinc fluoride, it's a product.
We need a different metaphor, like,
Remember the pumpkin pie thing that we had?
Yeah.
And that you could only make 4 pies because you only had, what was it? Yeah, we only had a certain number of cans of condensed milk, right? It was all dependent upon the fact that we had only 2 cups of sweetened condensed milk. That was the only thing that mattered. None of the other stuff mattered. So does it matter how much zinc you have if I'm gonna run out of my tin 4-fluoride? It doesn't. So all of that zinc is gonna be, you'll have leftover zinc. Some of it's gonna get used, but the moment that tin 4-fluoride runs out, I don't care that I have leftover zinc. It doesn't matter. Just like you didn't care that you had like 10 pounds of leftover flour for your pies. It doesn't matter. I can't make another pie because I don't have any milk.
And that's why it's not in the products, because it's not being used.
Right.
Right.
Yeah.
It's there, but it's just not.
It's there, but it's not one of the products. Right. So lithium iodide led to nitrate double replacement reaction. Okay. So I've got LiI, and that thing's going to be aqueous. And I've got lead 2 nitrate, and that's going to be aqueous. And if they swap partners, I'm going to get lithium nitrate, aqueous, and I'm going to get lead iodide, lead 2 iodide, solid. So I'm going to need a 2 here, I'm going to need a 2 here to balance that out. So this is reactions that happen in water, hence the full ionic and net ionic equations. How do I know that the lithium iodide is aqueous? Iodide has a rule, but lithium is the top rule. The top rule is group 1 metals are soluble. How do I know that the lead 2 nitrate is soluble? Because nitrate is the second rule that says they're soluble. So then when I mix those 4 ions together, they all get to bump into each other. And why, when the lead bumps into the iodide, does it form a solid?
Because iodine is higher on the lead is on the higher list of solubility, and
So
not.
lead's rule is higher on the list than the iodine rule, and the lead rule says it's insoluble. So when those 2 hit each other, they form a solid. So what does this aqueous thing here mean? That they're already solubilized, they're already dissolved. So I've got 2 lithium ions that are aqueous, and I've got 2 iodide ions that are aqueous, and I've got a lead that's got a +2 charge that's aqueous, and I've got 2 nitrates that are aqueous, and they're going to turn into 2 lithiums that are still aqueous, and 2 nitrates that are still aqueous, and then 1 lead iodide solid that's not aqueous. So in this problem, my spectator ions are which one? Nitrate for sure. What else? And the lithium. So those aren't going to be in my full ionic equation. So my full ionic, or my net ionic equation is just gonna be some lead that's aqueous and a couple of iodides that are aqueous, making lead to iodide that's solutes.
I have a question. I don't get why is it that you choose on the product side. How do you know which one to choose if you end up actually? I don't know how to explain it.
I guess about the ones that are highlighted.
Yeah, I do know why that they're the containers, but I don't understand why he wouldn't choose lithium with nitrate as the product and keep it together instead of the.
Because it's soluble.
Oh, so just the solids are the, okay.
The only thing that matters is did it turn into a solid or not. So when
I don't know.
I start with a lithium iodide that's in a test tube that's soluble, and I start with lead 2 nitrate in a test tube that's soluble, and then I dump them into a beaker together, okay? So then the lithiums, the iodides, the leads, and the nitrates can all bump into each other. So who bumps into each other and sticks? Just the lead and the iodide, that's it. Everybody else just keeps bumping into each other. So why didn't I put the lithium and the nitrate together and form a solid? Because they don't. All I'm doing is writing down what actually happens. And those things were aqueous in their test tubes, they were aqueous in the beaker, nothing ever happened to them. They were literally just hanging out,
So what if
spectating.
you have 2 aqueous products? What would you do then?
They're still aqueous. They're still sitting in that water. They're still going to stay dissolved.
There-
But what? Keep
There's no
going.
cases where there's no solids in the.
Then there'd be no product whatsoever. So we're going to talk about
What would
that.
I do?
We're going to
Okay.
talk about that lab. Yeah, we're going to talk about that lab. What would it take more to melt the ice or vaporize the water? So it's definitely going to take more to vaporize the water as opposed to melt the ice, because this is 540 calories per gram, and this here is only 80 calories per gram. So how much more heat? All right, well, it's 540 calories per every gram, and I've got 10 grams, so it's 5,400 calories, and that's to melt or to vaporize, and I've got 80 calories per gram and 10 grams, so that's 800 calories. So I do a little bit of subtraction, and I get 4,600. Takes 4,600 more calories to vaporize the water than it is to melt the ice.
Where did you get the calories from?
Where did I get that 540 and the 80? Those were on the out of the notes,
Oh.
and they were on that heating curve thing.
Are we gonna have to memorize it?
No. Have I had you guys memorize any numbers at all? Yeah. The 1,000 kilo is 1,000 and mega is 1,000,000, but that's it. No.
I'm mobile, you gotta know that, like, us and
Actually, I never told you you needed to memorize the 6.02 times 10 to the 23rd. Just know what it is.
Everybody's been using my flashcards, you can leave that around.
It'll make things go faster, for sure. Okay, so I've got a chunk of ice at negative 50 degrees Celsius, and I want to take it up to 120 degrees Celsius. So this is a heating curve problem, right? It's one of these up, flat, up, flat, up. And this is temp, and then this is heat added. So I've got this negative 50 degree chunk of ice. What do I need to do to it first if I wanted to get it up to 120 degrees? I needed to get it to 0. I don't melt it first. Before I can melt it, what do I have to do? I have to heat it up to its melting point, and then I can start to melt it. So the heat for this one, the Q, I'll call it Q1, is going to be the mass, which is 250 grams, times the specific heat, which in this case is a half a calorie per gram degree C. which is also out of the notes. And what's the temperature change? 50. It's 0 minus negative 50, which gives me a 50-degree temperature change. So I've got 250 times 50 divided by 2, 6250 calories. Okay, so what was that 6,250 calories doing?
Melting the ice.
No, it was not melting the ice.
Getting it?
No, it was starting to make them.
I haven't heard the answer yet.
Heating. Was it getting it?
Go ahead, Johns.
It was vibrating the molecules, breaking apart the intermediate.
Not breaking, just stick with your vibrating the particles more.
Yeah.
So the particles in any solid state, the particles are just sitting there in a fixed location, vibrating. And as I add heat while it's in its solid state, what is happening to those particles? They're vibrating faster. That's it. Am I breaking any intermolecular forces?
Not yet.
Nope. How do I know I'm not breaking intermolecular forces? Because the temp's going up, which means they're moving faster. So this section, I'm going from negative 50 up to 0, so the temperature is constantly going up, so I'm not breaking any intermolecular forces. I'm only making the molecule go faster. That's it. Anytime the temp change, what's happening to the molecule? It's moving faster. Nothing else. So I've got this, which is causing the molecules to all right, so now I've got this water up to 0. So now what can I start doing with it? I'm not going to heat it. Now I'm going to start to melt the water. So that's going to cost me 80 calories per gram, and I've got 250 grams. So 250 times 80. So what is this 20,000 calories doing?
Melting.
This is actually melting, and when we're melting something, what are we doing?
We're starting to
We're breaking apart the intermolecular forces, right? Okay. Now I have melted the entire ice cube, and this solid ice cube is now liquid. And so what do I need to do to it now?
Get it up to 100 degrees.
I need to raise its temp to 100. So I have my 250 calorie or grams. I'm going to, its specific heat is 1 calorie per gram degrees C, and I need to raise it 100 degrees Celsius. And so I've got 25000 calories. So what is this 25,000 calories being used to do? Say again?
Just to get them to it.
They're moving faster. What is this 25,000 calories definitely not doing? It's not boiling, not evaporating, not changing state. Okay, so Q4. So if I spend 540 calories for each gram, I can get this thing to vaporize. So that'll be 135,000 calories. So what's this 135,000 calories doing? Breaking intermolecular forces, right? So now it's at 100 degrees Celsius, and what am I going to do? Need to get it to 120. So my 250 grams, and it's back to that 0.5 calories per gram degrees C, and we're only going to increase its temperature 20 degrees. So 2500 calories. And what's this 2,500 calories being used for? So each time the temperature goes up, what am I doing to the molecules? Making them move faster. And each time the temperature doesn't go up, what am I doing? I'm breaking the intermolecular forces. Okay.